Wasteland Coder here again, and today we're going to talk about another couple of the solid design principles. Today we're going to take a look at the OpenClosed principle and the Liskov Substitution principle, because these two are also pretty closely related to each other. So if we take a look at OpenClosed first, this was introduced by Bertrand Meyer in his book Object-Oriented Software Construction, and it's defined as in the two parts of open and closed. So open is if a module is available for extension. For example, if it's possible to add fields to the data structures or new elements to the set of functions. So that's basically adding new behavior. Its module will be closed if it is available for use by other modules, and that the module is well defined and has a stable description. So, for example, it has a stable interface and hides the implementation details, basically. So if we dig into this, a lot of people will say a class can be still adhere to OpenClosed if you can just override it, which is kind of true. But in this case, here we have an unextensible class. It does some work, right? It just prints out does some work. So if we were to extend this class to give it some other work to do, such as different work, you have to extend that class and then override that method, which in this case you're basically rewriting the whole class. So it's not a very good example of an open-closed principle. It doesn't adhere to that very well at all. So this is a better example of it. We call it extensible. It has some behavior that we inject into it through the constructor or through a set method here, and then its doWork method just calls some method on that behavior, and then we have an interface for that behavior that we defined down here called enact. So now if you wanted to change the behavior of this class, you can just inject a different behavior. It's very open for extensibility, and it's closed because you don't have to actually get inside of this thing to do any modifications. You don't have to extend it like we did it in the other one. So then jumping along to the Liskov substitution, this one gets its name from Barbara Liskov and Jeanette Wing in their paper called A Behavioral Notion of Subtyping, and it's defined as this fairly, I'd say, ugly kind of formula here. But it basically comes down to if we have some property x on an object of t, or type of t, and some y of a type s, and then if x equals y, then s is a subtype of t. Or, other way around, if s is a subtype of t, x should equal y. They're both the same property. So if we take a look at an example of this, for an automobile, let's say we have one method on it called accelerate, and an automatic car and a manual car. They both implement their accelerate methods. The automatic car just increases the speed, prints out how fast it's going. The manual car increases its speed. It also has this condition to check for in here that throws an illegal state exception. If it's going too fast, basically, in first gear, it'll blow up the engine. And then it also prints out how fast it is going. Then it also has another method here for shifting and moving into the next gear. So if we run this, what we end up with is a class kind of like this. We get our cars. It's just going to be a list with a manual car and an automatic car. We just call them automobile since that's their interface. For each car, we just accelerate. We decide that's not going fast enough, so we accelerate again. Then, what happens when we run this? So, we get that the automatic car is going 10, manual car is also going 10, first time around. The second time we enter the loop, the automatic car, or the second loop that we enter, I should say, the automatic car now goes 20, as we expected, and then the manual car throws an exception, just like we expected, that the engine has exploded. Well, that's no good. How do we fix this? Well, one way would be to update our accelerate loop that we're going in, and then for each car, accelerate like normal. But then after we accelerate, if this is a manual car, shift. Well, that's one way to do it. But this does violate the Liskov substitution principle, because we do have to particularly care what type of car we are getting. We see this type of thing all the time in legacy code, that if instance of some class, do something special with that class. We know that's not good. A lot of times we can't figure out the right way to fix it though. In this case, it is one way to fix it would be to update our manual cars accelerate method, so that instead of just accelerating this or increasing the speed, we also check if we need to shift, and if we do, just shift right away. And then in this one, we've updated our statement that we print out to include the gear that we're in. If we do this approach, we end up with what we expect. Automatic car goes 10, manual cars go 10, in gear 1, 20, 20, and in gear 2. In that, with this approach, you don't have to modify the accelerator loop at all. We can go back to the old way, so that we treat each car the same. We don't have to care what type of automobile it is. We just do accelerate both times. That's it for OpenClosed and Liskov substitution. See you next time for the last one, dependency inversion.